I think it's particularly exciting to just have the choice and be able to target as effectively as you can a healthy life for your child.
Super excited to have Dr. Jerry Lanchbury on the podcast today. He's the previous chief scientific officer over at Myriad Genetics. He's led teams that were responsible for major molecular diagnostic innovations across oncology, urology, rheumatology, and neuroscience. He has had a really incredible track record in driving molecular genetic discovery from ideation all the way to translation into some high-value clinical diagnostics. So awesome to have you here today.
Thank you very much, Nora. It's lovely to be here and great to see you.
Yeah, thanks so much. Yeah, to kick things off, you just recently published a really cool opinion piece on basically why it takes so long for polygenic testing to make it to the clinic and why sometimes, or actually often, the pattern is that you see innovation and science get ahead of how difficult it is to actually educate clinicians. So do you want to give a little bit of context on hereditary cancer, the monogenic side overall, and then segue into kind of what the recent developments are on the PRS side?
Yeah, sure. I think what's been really exciting in the last 40 years, just to go back over a bit of history, is the realization that so much of cancer predisposition is actually down to genetics, and that many cancers are essentially a genetic disease with environmental factors piled on top. And I think in breast cancer particularly, and also in ovarian cancer and colon cancer, there's been great success, as you will know, in isolating monogenic factors which underlie familial breast cancer. But in the last 10, 15 years or so, and particularly in the last 5, we've turned our attention to the more common but less pronounced variation in the genome around SNPs, measured the effects of millions and millions of SNPs in women who are affected with breast cancer, produced these composite measurements called polygenic risk scores that enable us to then interrogate the genomes of healthy women and produce, alongside biological and clinical risk factors, algorithms that give a probability that woman over her lifetime or the next 5 years or the next 10 years might develop breast cancer. So these are probabilistic constructs. And so the testing scenario that has emerged from this is that you take a healthy woman with or without a family history, you apply either targeted sequencing, targeted panels, or whole genome sequencing, and figure out if this woman's carrying a high-risk mutation, an intermediate risk mutation, or whether she's carrying a constellation of SNPs that allow one to generate a PRS that determines their risk. And indeed, you can actually combine those risk PRSs with the determinations of high and intermediate risk genes and produce these kind of composite risks, which I think are very powerful. And I think that these have raced ahead in the field to the point where the technology exists and medicine really isn't ready for it. And I think that's been a little bit of a challenge.
Just to focus a bit more on the monogenic side, you talked a lot about these monogenic mutations, and I think it would be helpful to help orient folks to just talk about the difference in terms of the study design and the study sizes and why monogenic testing came first and basically why polygenic testing came second.
The monogenic discoveries really emerged from studies of families in the late 80s and the early 90s, where multiple cases of women with breast and ovarian cancer were found. And most of these studies were done in the United States. Some of them were done in Europe, particularly in England. And there were a number of groups that were attempting to isolate major genes underpinning this particular causation of multiple cases in families. And BRCA1 was discovered by Mark Skolnick's group. BRCA2 was discovered by Mike Stratton and independently by Mark Skolnick's groups. And those really started to explain these patterns of multiple inheritance of cancers that we saw in these multi-case families. So they came first because they were the strongest effects. And still in breast cancer and ovarian cancer, BRCA1 and BRCA2 have the highest penetrances of the underpinning genetic variation and the maximal effect on risk. And as other families with weaker family histories came to be analyzed, it became obvious that there were other genes that underpinned risks. And there's a whole slew, probably about 12, 13, 14 genes that are involved in high or intermediate risk determination in breast cancer. And the field has taken that as its starting point.
So basically, the really high risk, rare variants were discovered first because you have this really strong family history. Sequencing was expensive. It was hard to discover those specific families because they're by definition rare. And then as time went on, basically the study design transitioned because sequencing got cheaper and studies got larger to be able to develop these polygenic risk scores. So instead of looking at these single gene mutations that have very high effect, we're looking at anywhere from dozens to millions of variants that have cumulative effect on disease risk. And I think one really interesting point that you just touched on was how if you have a single gene variant like BRCA, you're the polygenic component of the risk, so not the single gene, but the cumulative effect across your genome can still modulate your risk. So could you speak a little bit about that?
Yeah, these were studies that were really done in the last 5 years, and they've concentrated on BRCA1, BRCA2, and also, I guess, PALB2, ATM, and CHEK2. So when one calculates a polygenic risk, you can see a modulating effect on the main risk according to the high and intermediate risk genes. And so there is some modulation of that risk by polygenes on BRCA1 and 2 risk, but where it's really profound are in the less penetrant genes like CHEK2 and ATM, and also PALB2. You can see really strong effect modulating there, where you up-risk individuals from the typical 2x, for example, for CHEK2, to maybe 3x or 3.5x, 4x. And also you down-modulate them to risks lower than the average risk for CHEK2. So the polygenic background is having a profound effect on these intermediate risk genes, which I think was a surprise to all of us, but gives us context going forward.
Yeah. So maybe to predict or to help think about how polygenic risk scores are going to be applied into clinical practice, maybe you could take us through a tour of how hereditary single gene testing made its way, right? So it first was discovered, I think, in 1995. So how did it make its way into clinical practice over the 2000s?
It made its way into clinical practice really through the commercial field. And part of the reason for that was the company that supported the cloning of BRCA1 and BRCA2 in the United States was able to file patents. It was able to protect its intellectual property. And then it was able to, in that context, put out those tests into the US market. And initially, with a startup, they plowed very large amounts of money into that, lost a lot of money on the testing. And I think for Myriad specifically, it wasn't until 2007 that they actually generated any profit. So they supported a lot of testing while the reimbursement came on board for that testing. So just to backtrack a little bit, many clinicians were extremely keen to use that technology. Many women who were in these families with multiple cases of breast and ovarian cancer wanted access to that technology. But it always takes some time for the reimbursement systems, both the public system of Medicare and also the private system with private insurers in the US, to catch up, to appreciate the evidence base, for scientists and clinicians to accumulate that evidence base, and for those two to then come together, and for the insurers to actually pay for the tests. That was a very long history with BRCA1 and 2. And I think we're seeing the same thing again with polygenic risk scores, whereas as far as I know, polygenic risk scores are not reimbursed either by the public insurers in the US or by private insurers yet. And I'm sure that's just a question of accumulating enough evidence to convince insurers to do that and to convince them of the value of the tests.
And can you talk a little bit more about the evidence for PRS?
Just looking back historically, there were PRSs in the market prior to the PRS that Myriad put out. It's just they didn't get real traction for a number of reasons. And one of those reasons was they didn't necessarily work in women of all ancestries, and they weren't necessarily calibrated for women with family history, for example. So if you look generally, there are many research groups around the world who've made important contributions to the science of PRS testing in breast cancer, ovarian cancer, but also in prostate cancer and colon cancer. And as we said, it just takes a while for the field to develop the evidence base and then really appreciate the evidence base. And we're in that process at the moment. The markers that we use in the PRSs, most of them, if not the vast majority, are not actually causal markers. One isn't actually measuring the underlying genetics that determines the functional aspects of the disease. What we're doing is we're measuring indirect markers that are linked to the functional markers through linkage disequilibrium. And linkage disequilibrium is a kind of function of population history. If you go way back in time, the vast majority of variation on the planet was actually generated within Africa. And Africa is the cradle of humanity. And so most of the diversity of human beings actually exists in Africa. But there was at least several out of Africa events, several migrations that carried DNA and carried genomes and carried variation with them. And so at least one estimate is that that founding group of the rest of the human population set was maybe down to 1,000, 1,400 individuals. So that was quite a small sample of variation.
Yeah. I think that's a shocking number. I think even if you said it was 10,000 or 100,000, most people would think that's crazy. There's billions of people around today. Do you want to talk a little bit about hereditary cancer more broadly, the other cancers besides breast cancer, just to give people a taste of what's going on there?
Yeah, it's very much the same story with fewer numbers, and this is a numbers game. It is very data-driven. And also some of the effects are less marked in other cancers. But if you take BRCA1 and 2, for example, they have effects in prostate cancer, they have effects in pancreatic cancer, they have effects in ovarian cancer. And in pretty much all those cancers, there are potential modulation of PRS as well as risk definition according to those markers themselves. And not just that, it's not just important in unaffected men and women in defining risks that are relevant to their sex. It's also important in treatment. And also in the last 15 years or so, we've seen the development of PARP inhibitors, which initially were approved for use in BRCA1 and 2 carriers, initially with ovarian cancer, but now are being generalized to a number of cancers. So because of the specific DNA repair mechanisms that are distorted in carriers of those genes who develop tumors, this particular class of cancer therapeutics, targeted cancer therapeutics, which are the poly-ADP ribose polymerase inhibitors, they actually work much better in individuals that carry those mutations. Not only are these mutations useful for predicting risk in unaffected individuals, but they also support very targeted modalities of therapy in people who carry them, who have developed tumors.
A summary of the situation is that in all cancers, there's a minority of individuals who have a rare, monogenic, highly penetrant mutation, and the vast majority of other people do not have one of these mutations, but their polygenic risk, so that cumulative risk across the genome can stratify and help them identify if they're in that tail of the distribution where they're at higher risk. But that's not all the explanatory power. Obviously, there's still a lot of unknowns. That there's cancers that are, basically individuals who have monogenic mutations, but they don't go on to develop the disease. And there's individuals who have high polygenic risk scores who don't go on to develop the disease because of unknown environmental or lifestyle factors. Do you want to comment a little bit about that, about these anomalous cases where the evidence suggests that they should get the disease, but they don't, and why that might be?
I think the essence of it all is this is a probabilistic environment, and it's hugely frustrating to not be able to understand the entirety of whatever model is relevant to these situations. But in familial breast cancer, for example, I think we have enough markers, we have enough clinical and biological data to explain about 50% of the propensity for risk, which means there's another 50% and many careers left to figure out that other 50%. I think you said a really important thing, which is in women who don't carry monogenic mutations, PRSs enable you to put them somewhere on the risk spectrum. And PRSs are actually relevant to everyone and not just women who exist in families with multiple cases of breast cancer or other cancers indeed.
Because most people who develop cancer, they don't have a family history. The vast majority don't,
Absolutely,
right? So
yeah.
being able to stratify your genetic risk, because it can double or triple your risk depending on how high it is, super useful even if you don't have a family member that's been affected.
Absolutely.
And it's not just cancers, but it's outside of cancers, pretty much any complex disease. Complex meaning, are there multiple genetic factors that are driving it? So what is your prediction, or what do you expect the path to be forward in terms of physicians and insurance companies getting up to speed with polygenic risk and the value that it has to patients on this risk mitigation journey, essentially?
You said before that many hundreds of thousands of women have already been offered this technology, and their physicians have received data, and they've been able to have effective and meaningful conversations around those data. That's not to say that everyone has been screened by any sense whatsoever. That's not true. But at least some work has been done, and clinicians have taken that technology on board. I'm not aware of the fact that technology has specifically been paid for yet by insurers, but I'm sure that's a prospect that will occur within the next 5 years as insurers get more comfortable with the data, as more of that data is generated, and as more physicians generate evidence and advocate within their professional societies for insurance pay for this data, because I do think they're very powerful, and I think that situation will pertain.
Got it. Yeah. And I guess switching gears a little bit to there's all of us who are alive today, our genetics are fixed. When we have kids, we have this opportunity for the first time ever to actually mitigate risk in the next generation. So do you want to speak a little bit about embryo screening and what excites you about polygenic embryo screening?
I think what's really interesting there is this ability to, if you like, tailor the family that you're going to have, because most of us only have a small number of children in our lives. And we invest all sorts of resources and love and care and attention. And I think particularly for women and men who are in families where high risk and intermediate risk genes are segregating, it's exciting that they have the opportunity to make choices about whether they do or don't pass those mutations onto their children through embryo screening. And you're a world expert in that area, Noor, and have done great work there. So I think it's particularly exciting to just have the choice and be able to target as effectively as you can a healthy life for your child. I think what we're learning is that the same kind of technology around polygenic risk scores that we can apply in adult populations also can be applied in defining potential cancer risk in the embryo stage.
Yeah, exactly. And the other side of it that I think is really cool is beyond the polygenic risk, there's also the monogenic risk. So when you're screening the entire embryo, you have obviously all of the SNPs that you want for any polygenic risk score, but you also have all of these monogenic variants. So I'm just curious, your commentary there on basically the monogenic side compared to the polygenic side and how parents should be thinking about that and weighing the options.
Yeah, I think the powerful thing is to be provided with that information as a parent and to make an informed choice based on the data that exists, based on what we know about the translation of those genetics to cancer risk in adults, which enables informed choice to be made. I think it's very powerful, and we're at an exciting stage in the field to be able to make those decisions.
What would your advice be to patients in general about how to learn more about this and about how it can impact their health, whether they've already had kids, whether they're having kids? What do you think are some of the resources that are useful to help understand all of this information?
I think in terms of genetic risk of developing cancer and breast and ovarian cancer in particular, there are great online resources with Susan Komen and Force and the NIH in the US. And women should, and I'm not a clinician, I'm a scientist, but obviously women should talk to their family practitioners and their OBGYNs. And if their OBGYNs aren't sufficiently informed, then they can obviously have a further conversation and they can do more research on the web and come back and have a richer conversation, perhaps. But there is an enormous amount of information out there. There is a great ability to understand the risks in your future and how you might deal with them and mitigate them in a conversation with one's clinician.
Can you chat a little bit about genetic counselors and what their role is in all of this?
I think what emerges from this conversation is how complicated all of this is. And genetic counselors are experts in genetics, which most doctors aren't, frankly. And the genetic counselor is an expert conduit who can talk to a patient, for example, if they come from a family with a high-risk background. They can discuss the pros and cons of genetic testing with them. They can discuss the implications of testing should they prove to be positive or indeed negative. And so they tend to work with physicians to complement testing and to help with aspects of the testing that may be hard for members of the public to understand.
Yeah, I think one of those aspects is just what is the difference between a lot of these technologies, right? What are the kind of the basics of the types of sequencing that's available, the types of interpretation that's available to help patients make sense of what the differences are.
Yeah, I think if you're an expert in the field, looking at a product like 23andMe's product, you understand both its strengths and its limitations. And prior to a few weeks ago, it essentially interrogated 3 mutations in BRCA1 and 2, which were the classic Ashkenazi founder mutations. Quite recently, they had an upgrade, and I think they now do 63 specific BRCA1 and 2 mutations. But there are tens of thousands of these mutations just in BRCA1 and 2. And so the only way to really get a proper interpretation that is as foolproof as it can be is to have a full panel test or to have a full genome test that is clinically validated. And an expert such as a genetic counselor can help women and men understand both the strengths and the limitations of the consumer tests, even if those consumer tests happen to have some FDA stamp on them.
Yeah, maybe could you comment a little bit about the difference between panels, why panels have different sizes, and compare that to whole genome or whole exome and what that means?
I think panels historically have different sizes because sequencing has been expensive and costs have been pushed back on by insurers. Ultimately, it could be an all-you-can-eat buffet, and the whole genome sequence properly annotated and properly analyzed gives you the best opportunity that you can have to understand your risk factors, both at that monogenic and that polygenic level. It's just we're on this sort of emerging pathway where the first tests you could get done were BRCA1 and 2, and now there are panels of multiple 10 scores and hundreds of genes that are interrogated for risk. And as if you're going to have a cancer panel done, then you might as well have a cardiovascular panel done, and you might as well have a structural biology panel done, and you might as well have a neurological panel done. Otherwise, you just keep coming back. But I think with the power of technology, we are arriving at a point where you can just have a one and done evaluation, and you can carry your file around for the rest of your life. And as more risk factors at the DNA level are ascertained, you can go back to that file and have those evaluated. And I think that's very exciting for all of us.
In this paper, I think you've done a really good job of representing both sides. What is the criticism about PRS? What is the response? And why has that response not really been fully engaged with? So maybe do you want to talk a little bit about those 2 points on
Yeah.
the opposing side, and then also on what the responses to those concerns might be?
Yeah, I think on the opposing side, number one, this is new technology and people have to wrap their arms around it. They have to use it. They have to get to know it, to trust it. I think until the clinicians have done that and have learned to trust it through use, it's hard for them to then have a confident conversation with a patient in the room. And that's all fully understandable. And I'm not trying to be condescending at all. I can appreciate the difficulties when you're on the front line and on the bleeding edge. I think the second thing is the performance is not the same in every woman of every ancestry. But I think the performance is good enough in every woman of any ancestry to offer net benefit for a healthy woman in terms of her risk prediction. And so I think in the pursuit of equality across different groups, it's important that we make the best of the technology that we have rather than wait for a perfect world that may be impossible to achieve. It may be that biologically we have to sequence everyone in Africa to get something that works as well in African women as the tools that we have work in European women. Or it could be unattainable in our lifetimes. And so I think my point of view in terms of being a developer of these tools in the past is that we're really doing the best job for every woman that we can. And I think even the most compromised performance in the most difficult group to ascertain genetic risk in is still good enough to offer a tool.
Yeah, I totally agree. I think something that's really often missed in this conversation is what is the next best alternative? If you look at just birth outcomes or C-section rates or literally any outcome in clinical medicine, whether it's a procedure or whether it's a drug, the performance is not exactly the same in everyone. It's not the same in men and women. It's not the same within different age groups. It's not the same within different ancestries. So I think the whole practice of science and medicine is do the best that you can with what you have at the time. And it seems bizarre to hold something back, because some of these are, I would say, historical artifacts that are outside of our control. This founder event from Africa, there is more diversity there than there is outside of the rest of the world. That's not something anyone can do about. But obviously, the fact that historically the countries that invested the most in sequencing were of European ancestry, and there wasn't more force given to collecting equivalent databases than others may have been something that people could have pushed for harder. Doesn't mean that today, with the data that we have, we should use it to the best of the ability that we can.
Yeah, and I agree with you completely. And I think my fundamental point is that these tools actually offer something of benefit to everyone, even though that benefit might not be equivalent. And therefore, I think it's just morally wrong and ethically unreasonable to sit on them for another 20 or 30 years until they're perfect, because we don't know whether they can be perfect.
Do you want to talk a little bit about PRS maybe more broadly than cancer? Are there any other diseases or other areas or other research that you find exciting that you want people to know about?
Yeah, I think the PRSs in cardiovascular disease are really interesting and quite compelling. And I think the question there is whether they add to the clinical factors that are ascertained in clinical practice, whether they augment that. And those questions, I think, are in the process of being answered. There are really interesting PRSs in metabolic diseases. We've seen them in type 1 diabetes, type 2 diabetes, for example. I think they're powerful there. And so there's a kind of trickle-down effect there, all the way from, I would say, breast cancer, which is the best use case, down through cardiovascular disease, colon cancer, prostate cancer, and as we increase numbers into some of the other rarer cancers, all the way into other phenotypes, which may be less clinical, but also may be of interest to people. And so I think there's a kind of dividing line somewhere in the middle between clinically informative and clinically actionable PRSs and other PRSs which are scientifically valid, but which are just of interest to people and might not be clinically actionable, shall we say.
Yeah, I think that clinical actionability is a really interesting piece, right? So this is, how is it going to change management? What are you going to do differently now that you have this information? And interestingly, the question is actually more complicated for adults than it is for embryos, right? So for embryos, if you're fortunate enough, you have multiple embryos and you have to choose to transfer one of them. Most people aren't going to have 10 children or 5 children in a short period, so they have to choose to transfer one. And the decision is simply just to minimize risk. Versus an adult, it's actually more complicated, because if you have a very extensive family history, you might choose to have a prophylactic mastectomy. There's so many different types of interventions that people have actually done, which have much more severe impacts on their life, and there are actually much more immediate medical decisions that need to be made. So I think that's also a huge piece of what kind of drives the adoption, right? If there's something very specific and a very clear next step, okay, do mammograms twice as often, or take this drug 10 years earlier, maybe in the case of cardiovascular disease, take statins sooner. What is your thinking around the actionability and how that drives basically physicians in that field to either embrace or be dissuaded from offering PRS to their patients?
I think you've talked about two different scenarios, if you like. One is the patient in front of the doctor, where that patient is making a choice that affects their health and their life outcomes. And that scenario in the reproductive clinic, where you're really making a choice about your children's future risk to a large extent, and to your legacy, if you like, because your DNA is going to go on generation after generation. I think you've hit upon two really interesting clinical scenarios, and I guess in my scientific work, I've really been mostly involved in work around the woman that sits in front of the doctor and offering her and the doctor the maximum information possible. And the other scenario, the one that you talked about in the fertility clinic or the reproductive clinic, is a science that's just starting to become possible and has huge numbers of opportunities to offer. And I guess we're just starting to get to grips with that.
What would you say the biggest misconception physicians have about polygenic risk is?
I just think it's hard to come to terms with the fact that these are statistical models that involve hundreds, thousands, tens of thousands, hundreds of thousands of markers with tiny effects. It's hard to get your head around it. It's like looking up into the Milky Way at night and taking all of those stars on board and thinking about the cumulative intensity of them, or the cumulative gravitational pull of all of those stars. And I've never thought about that analogy before, and it's just struck me now. it's hard to get your mind around those tens of thousands, hundreds of thousands of individual data points and to extrapolate from them. I can understand why conceptually, if you haven't grown up in an educational environment where apologetics was part of the bread and butter, that it can be hard to take that on board.
Yeah, it's a complete and utter paradigm shift. Pivoting to patients, what do you think the biggest misconceptions patients have about genetics is?
I think one of the big misconceptions that people have is, if you like, the deterministic aspect that, if I
Mhm.
have this thing, then X is going to happen to me. And there's not always the appreciation that this is a probabilistic model and that X won't necessarily happen to you, but you exist on some sliding scale of risk and you can choose to make a decision or not make a decision with your physician. I think a lot of people, unfortunately, have a hard time figuring out probabilities and exactly what they mean. And so I think that's part of what's hard to take on board.
What about for the statistical genetics or scientific community? What do you think their biggest misconception is about polygenic risk?
I think the statistical community is actually very strong, and a lot of the people that I interact with, they're all mutually supportive in a way. I think one of the problems that they have is that transition from monogenic disorders, and the genes behind them have been around for, the disorders have been around forever, and the genes have been around for 25, 30 years, and we've had that understanding of them. I think there is a big difficulty in transitioning to an understanding that there is a precision associated with PRSs that in some ways is more precise than the risk that is associated with some of these monogenic determinants.
That's a really good point that people don't touch on. That's actually true because you have hundreds of thousands of individuals and you can see their empirical what is their rate of disease versus by definition, if you're looking at a rare mutation, you don't have as large of an N. That's
Right.
actually a good point.
And one of the ways that's articulated, Nora, is that with BRCA1 and 2, for example, but BRCA1, say, we talk about a lifetime risk of up to 80% of developing breast cancer. We don't actually give an exact probability with, if you like, confidence intervals, but we can take a woman with a clinical PRS model and we can say, you've got a 35% chance of developing breast cancer in your lifetime, plus or minus 2%. And actually, in that sense, the risk that we're giving is at least more accurate in its calculation than the risk we give for a BRCA carrier, because there we give them the worst possible scenario, which really informs the conversation. And I still think that's a problem. I still think people have to appreciate the difference between the up to 80% and, say, the 35% risk, and really take that on board and translate that into the way that care is given.
Great. This is a really amazing discussion that kind of covered everything from the history of cancer genetics all the way to what we can expect in the future. So it was amazing to have you, and thank you so much for joining us.